Hello. It is that very time that I have calculated the total energy of the whole universe, that it includes the contributions of the photons, the energy densities of photons, neutrinos, and non-relativistic matters density in the whole universe. So, I intend to present it assiduously, by the way, and it will be, I hope, a short video. So here's the calculation, a little bit different, and we just derived the equations for the Friedmann equations, second order Friedmann equation actually I have used, and afterwards the first one, first order, and we just differentiated those equations respectfully to the time. And afterwards, what we did is actually we intended to take a look into the relation between the energy density of radiation and non-relativistic matter respectfully to time, because there was a shell, a Gaussian surface, doesn't matter what it is. The importance is that this shell, or maybe the field, is filled with the radiation densities, or maybe non-relativistic matter densities. So the importance is that this field is actually going to be expanded. So the density per unit area or the surface doesn't matter. Or important is that it is going to be volume is going to be decreased by a factor of a to the fourth or maybe a to the third. So by using such a relation, that's the first assumption is going to be wrong. It is going to be disproved, right? So the first is actually when you derive this equation, let me switch the camera. Okay, this place is what I'm talking about. So we are just writing down total energy in the whole universe in here. U of t is the total energy, rho is the density, total energy density, times c squared, c is the speed of light, and v sub p is actually the physical volume of the system. So I think I remove it from here. This is actually the afterwards volume of the system, actually not the volume, not the system, sorry. This is the spare's volume, which expanded by a factor of a to the third, as you can see here. And this is the coordinate volume, the first volume, which is a constant number that you have measured in the rest time. For example, t equals t naught. So if we derive this equation respectfully to the time in here, du of t divided by dt, here there's a derivation, so you are just, it is easy actually, not that hard. Du divided by dt equals de divided by dt, the same things, is rho dot a cube of t, a cube of d vc c squared, plus dot, and here is it's just a derivation. Okay, this is mathematics, not physics right now. And same, we are just divide both sides by a cube, and what we get is important term here. So this is what we have in here. You can calculate it. So I'm just writing down the first order Friedmann equations, which respectfully solve for the field of matter here, and which is as a function of time. So k is the curvature of the space, or maybe the metric that you are working. So in this assumption, we did not accept, or maybe we didn't let the curvature is to be 0 unless, sorry, instead of it, we didn't remove it in here, because the space can be open or maybe closed. So it corresponds plus or minus k, not 0, okay? 0 is the easiest solution, which is the flat case of the universe. So I just solved for the first time derivation of the a of t here, a of t squared as a first time derivation, and first order, second degree, right? Some constant here, and rho of t, a squared, t minus kc squared. So what we get, again, this term. So I just distribute it along this place. So I differentiate this equation respectfully to time. This gives. So the importance is this term. How do we solve it? So if you take the radiation-dominated era of the universe, that you have to solve the equation which the density of non-relativistic matter decreases by a factor of 1 over a cube. So rho m0 is actually the first actual mass density, non-relativistic mass density of the universe. So respectfully, if you derive this equation, so this is rho dot, okay, this is rho dot, you can find out how the derivation of the non-relativistic matter density behaves in my previous video, which is the inflationary cosmology. So the first derivation of it, rho's non-relativistic matter, so the first time derivation of it, okay, the first relation is some constant rho m0 divided by a cube of t. So the first time derivative of it, rho dot, let's say the first time derivative, so it becomes minus 3 a dot of t and rho m0 divided by a to the 4th. And you can rewrite it by a Hubble factor, and it gives such this relation here, as you can see. And the first integration is done, sorry, that derivation is done. And the second one is the derivation of the a of t in here. And what I get is actually here, 2 times rho m0 divided by a cube t, a of t, a dot t. So the order is just decreased, 1 decreased, okay, 1 minus, which means. So you are just solving it and some diligent calculations. This is not a calculation actually, this is just a mathematics. There's no something special here, just a differentiation. Even we don't solve the differential equation, which is second order. So what you get here, a double dot equals minus 4 pi g divided by 3 rho of t times a of t. This is what we have to see, what we must see, because we were expecting to find out such a value like that. And in my previous cases that you can easily find out that the expansion of the gravitational field, because of the expansion of the universe, because of the inflation, because of the kinetic energy, that it becomes non-stationary gravitational field that accelerates towards the future as time itself ellipses expeditiously. So a double dot is the ratio of the acceleration of this shell, which we were investigating as the globular cluster, right? So the radius of the globular cluster in here, which is like a sphere, is going to be increasing by a factor of some constant, okay? So this constant is actually the scale factor, not a constant. So this is something true for non-relativistic matter. But when the when the solution time for the radiation case, the radiation dominated case, you just put into the equations that the density of radiation is decreasing by a factor of a to the 4th, okay? So this is rho radiation 0. This is the actual radiation density of your first measurement towards the system. So it is actually the actual radiation density of the whole universe at t equals t naught, okay? So this let it stay here. If you derive this respectfully to time, so rho dot, the first time derivation of it, becomes minus 4 rho r0 a dot divided by a to the 5 as a functions of time, respectfully. So you can easily write it down like a Hubble constant or Hubble function, not constant, and you just put it into here. We are solving again for the rho of t and rho dot of t, and what you get, a double dots, a dot is the first time derivation, first order and second order. 8 pi g divided by 3, some constant, we can neglect it for some time, for some precious time, for the sake of the C, that very relation that I intend to find out between the density of radiation and the scale factor. Here is what I get. You just replace it here. You just cancel each terms. So for example, a dot cancels the other side. In the right hand side, a dots stencils. They remove, I'm not sure the true pronunciation of it. And what we get, a double dot equals 8 pi g divided by 3 rows of r divided by a cube of t. This is what we intended to see. As you can see, it is not consistent with that one. But the relation between them is that the expansion of the universe, the rate of the radiation-dominated universe is 2 times the non-relativistic matter-dominated universe. This is actually the scale factor and this second time derivation of it. This is something interesting, that the model is not consistent from the classical calculation of Friedmann equations. Exception is the non-relativistic matter. It works nicely, but it is not. These are not equal each other. There is no equivalent between them. In my next cosmology video, I will derive this equation again with more, let me say, we will focus on exactly as I did in my previous cases. So it will take 1 or 2 hours to record this video. I just, today, for today's sake, I just wanted to show you, because I did it right now, like 1 hour ago, I completed this theoretical calculation, which I have first seen in the MIT's lecture, the professor, Alan Harvey Guth, that he gave an homework towards the students, and these are just the equations, or maybe the way of solution. He just gave in that very lecture this solution, and he said that those both consequences are not consistent from what we predicted from the second order Friedmann equation there. So, okay, I got it closed for now, and see you then in the next cosmology video that we will prove the dynamics of the universe, and afterwards we will solve the equations. And by the way, some assumptions that's going to be needed